would like to know.
Struggling into the latest shuttle suit isn't easy. Made from thick layers of advanced materials and fixed with hard joints, it is more like a miniature spacecraft than clothing. Susan Shentrup is a spacesuit technician. Her average size, fitness and technical skills make her an ideal guinea pig when a reconditioned suit needs a test.
All right, underneath the lower torso, you see she's got a cooling garment on. She's going to put on thumb loops.
The tight-fitting cooling garment is a British invention from the 50s, originally for fighter pilots.
That makes sure their garment doesn't get bunched up on her shoulders. And she absolutely just dives through, puts her arms up and pushes with her legs straight up into the hut, or the hard upper torso. All right, she's up inside. First thing we're going to do is get her a little cooling, so she hooks up the garment to the backpack, locks in place.
This belt-like clip is a hose connector that joins the pipes laced through the cooling garment to a cold water supply on her backpack.
She's going to use these donning handles. She brings it up in line, lines it up. So we need to line it up. All right. Drive it up into the locks. And there we're all set.
Okay, next we don the communication cap. Adjust the chin strap under the chin. Make sure the microphones are up close against my mouth. Okay.
All right, next step is put on the gloves.
The gloves need to stop a bullet and pick up a dime, say the astronauts. But NASA has never cracked the problem of gloves. They remain bulky, uncomfortable, and inhibit dexterity.
She can't inadvertently come off in space, so there's a lock and a secondary lock behind that. It takes two hands to get them open. The hand in space, so the gloves are the trickiest part of the suit. Okay. So she's got an ability to tighten up the gloves to fit her hands. That's what she's doing there. And we'll turn on the, put on the helmet, get her buttoned up. All right, the helmet locks in place just like the other garments. She lines that up, drives it down, and she can lock it in place. And she's ready to go outside. So we're going to take her off the wall.
The shuttle suit weighs over 250 pounds. This cumbersome suit is all that NASA can offer its astronaut in space.
Use out space are the helmet visors.
It is a triumph, not of science, but of engineering. A culmination of a 50-year struggle to live outside the protection of Earth's atmosphere. A mere 30 years from now, the US administration expects Americans to step onto the surface of Mars. For that, this suit is useless. So where does NASA go from here? And how did it get here in the first place? The year is 1959, and America's first 7 astronauts line up for the group photograph. Afterwards, John Glenn, perhaps the embodiment of the crew-cut all-American space hero, climbs aboard an Air Force fighter. Glenn and his fellow Mercury astronauts are pilots. For their first journeys into space, they will wear little more than a Navy pilot's pressure suit.
As far as the Navy suit is concerned, very little was done to make it applicable for the Mercury configuration. We changed some of the materials. We used lighter weight materials. We used an aluminized version of that material to jazz it up, if you will. There were no real requirements for having, as far as I remember, an aluminized outer garment. But it looked good. It did make it different from the Navy version, and the entire suit was lighter.
The suit would expand, pressurize you, keep you in a safe atmosphere until you got down to a lower altitude where the suit would deflate again, and there you were just like flying in a flight suit.
It was a suit simply to provide backup protection in the event the cabin lost pressure.
America's first space pilot, Alan Shepard, knows that this is all he can expect from his silver-coated suit. It might get him home if his tiny Mercury capsule loses pressure, but it is doubtful. Prior to flight, all suits were tested for leaks. At 5 pounds per square inch of pressure, the suit goes stiff, like a pumped-up car tire, but in the shape of a man.
It formed the shape of a man in a seated position with his hands in a relatively neutral position, such as this, and his legs pretty much in a seated position.
But the Mercury pilots will never use these so-called get-me-down spacesuits pressurized. Every flight succeeds, so the silver suits are worn deflated and soft, just as they were in fighter jets. On Earth, we live unaware of our own natural fleshy spacesuits. Muscular power pressurizes us, keeping everything in place, pressurizing the blood, squeezing the internal organs, and inflating our lungs. All around us is pressurized gas. We call it air, but it is heavy, at sea level weighing over 14 pounds per square inch. This weight forces air into us, helping us breathe, so we don't have to gasp to get oxygen from the air. Two things happen as we climb above sea level. We breathe more heavily as the air gets thinner, and our bodies expand as internal pressure overpowers the lighter atmosphere. Once in space, there is no air, and our pressurized bodies, released from counteractive atmospheric pressure, would simply explode as our blood boiled. So at a minimum, a spacesuit must provide breathable oxygen and sufficient pressure to stop our bodies inflating. It was the high-flying American, Wiley Post, who in 1934 first wore a pressure suit for altitude record attempts. He discovered that when his soft rubber suit was pressurized, it became hard and immobile. Before Wiley Post can try the suit, he is killed in a plane crash.
You could look at a spacesuit as encapsulating the body in a balloon. And the pressure comes from the inflation of the spacesuit to provide an adequate pressure around the body that's required for survival, in particular in a vacuum of space. The problem comes in trying to shape that balloon to the anthropomorphic dimensions of the body, such that where you have joints at your shoulder and your elbows and knees and waist, you can achieve mobility of the joints such that you can do productive tasks through body movement. So the pressurization that's required to pressurize a suit acts as a force that the astronaut must overcome in moving the joints of the suit.
Once America's two-man Gemini program is underway, the requirements of the spacesuit change dramatically. The astronauts will no longer sit passively at the controls. They will open the hatch and tumble into space. Known as extravehicular activity, or EVA, it becomes clear that the immobilizing pressure will be the main obstacle to useful work in space. This is astronaut Ed White. He can barely move. A stiff wave is about the limit of his action. To investigate the problem, a complete EVA simulation had been developed in huge underwater tanks. They mimicked with uncanny accuracy the stiff immobility of the Gemini suits in space. Soon, answers are found. Called constant volume joints, they transform the performance of the astronauts with bellows-like hinges at critical points.
Picture an accordion. You play music, you open it like a fan, and the bottom squeezes, and the top expands, such that you're keeping a constant volume. The pressure that's expended squeezing the bottom is alleviated by spreading in the additional volume at the top. So the constant volume joint was the answer to good mobility in the suit.
But the exuberant publicity stunt of football on Earth, in a suit with constant volume joints at 4 pounds per square inch, hardly compares with the exhausting rigidity the astronaut has to overcome when this pressure expands against the vacuum on the surface of the Moon. The age of Apollo was the high point of suit research. With money no object, outrageous and practical answers were offered. Mars was to be colonized in the mid-80s. America was in the frontier business again. Back on Earth, the business of spacesuit construction was somewhat less romantic. With the vast American military-industrial complex to draw on, it seems odd that a sleepy town in Delaware should become home to the uniform of the American space hero. Just outside the town of Dover is ILC, once known as International Latex Corporation, and before that part of Playtex, the living bra people. Sole contractors for all US spacesuits since Apollo, ILC used the corsetry skills of lady seamstresses to ensure absolute integrity. Cut and sewn to a tolerance of 1/16 of an inch, one needle hole in the wrong place means back to the start on any one of the 11 layers of the shuttle suit.
The innermost layer is a LCVG garment, liquid cooling and ventilation garment. It's made of 2 basic materials. The innermost layer of that garment is a nylon material. It helps wick the moisture away from the body and keep the crewman comfortable. The next layer is a spandex material, and this is so that it fits very well and conformal to his body, and there's some EVA tubing that's strung through that. The function of the tubing is to carry water through the spacesuit to cool the astronaut. The next layer is the bladder material. It's a nylon material with a polyurethane coating. The next layer is the structural layer of the suit. It's the polyester or Dacron layer, and it's the major structural layer. The outermost layer is a composite of a number of materials, and it's called the TMG. This layer is a neoprene-coated nylon material, and it's the micrometeoroid layer, and its function is to stop the micrometeoroid impacts. The next 5 layers are the thermal layers, and this is an aluminized mylar material. It has a nylon scrim on the backside, and the scrim acts as a standoff to create a vacuum in between the layers to protect from thermal. The outermost layer is called an ortho fabric. It's made of Kevlar, Nomex, and Teflon. It's a very flexible material, and it's the outside protective layer of the suit.
The NASA spacesuit has evolved layers of material through stages of development to the thick and heavy space vehicle it is today. but it remains a distant cousin of the original Mercury suit.
The big problem in Mercury was comfort, unpressurized. Today in shuttle, the problem is making sure we don't have any kind of problems that could cause an abort of the mission that you are trying to achieve or loss of life of an astronaut. Because it is, when you're in a spacewalk, you're right out there, and there's very little thickness of material in the bladder and restraint between you and the vacuum.
Apart from sheer material strength, there are more complex reasons for the bulk of today's shuttle suit. Inside the shuttle's cargo bay, temperatures can reach 121 degrees centigrade, and yet on its dark side can drop to minus 157 degrees. In addition to this, the working astronaut is creating heat too.
The human body acts like a flame. It produces heat, at least 100 watts, equivalent to a 100-watt bulb when you're just practically asleep. Could be 10, 15 times that much when you're doing exercise. So that heat is being pumped into the spacesuit. The spacesuit's like a thermos bottle. It's heating up. If we didn't remove the heat that built up inside that thermos bottle, you'd cook them.
So cooking is what they did. Astronauts worked for hours inside suits under heat lamps to make sure death through exhaustion couldn't happen. Even today, the simple British underwear with its piped cooling water still works perfectly under all conditions.
The heat was picked up that was generated on the skin by these pipes, precluding, therefore, perspiration, so that for a finite period of time, and it ran anywhere from 4 to 6 and maybe emergency 7 hours, where you could work hard and not perspire. And for certain periods of time, you could work at a rate of 2,000 BTU per hour, which is extremely high, equivalent to the soaring down of a tree in the tropics, and you would not perspire.
It's got to be one of the most proud moments of my life, I guarantee you.
The moon was the real test. The bulky backpack, or portable life support system, known as a PLIS, carried cooling water, batteries, oxygen, and all the electronics for a 7-hour EVA.
Let me put some weight here.
The PLIS was a miracle of mid-60s technology, and coupled to the suit, remains a target for weight and reliability today.
The lightest suit we've ever built, which was the Apollo suit, in recent times that is, weighed 220 pounds. And on the moon, with 1/6 gravity, that ended up being a nice 37 pounds equivalent weight that you carry on your back. If you were to take that suit and put it on Mars, it would weigh 80-somewhat pounds. It would just be way too heavy to walk around in. Now, that was the Apollo suit. Now, since then, we've evolved through all the bells and whistles and everything else that we've wanted to put on to a suit that's approaching 300 pounds, and projected space station suits are, you hear, anywhere from 350 up to, God knows, 500 pounds. So clearly, in terms of the weights, they're completely unacceptable.
Outside the shuttle, leg movement is unnecessary. Work is done with the arms. The legs float free. So these already heavy suits do not have some of the joints that would be needed for walking and bending.
The shuttle suit was designed for Earth orbit application where there's no requirement to walk on any surface, under any gravity field. And as a result, we did not incorporate unique joints in the lower torso or the pants section of the shuttle suit because that is expensive and it adds weight and complexity that's not necessary. So there was a conscious decision not to incorporate the best mobility features that were present in the Apollo suit in the shuttle suit because it wasn't necessary.
All current work in space is so-called upper torso effort. This upper torso effort is in marked contrast to the activity on the surface of a planet, where walking, or on the surface of the moon, so-called bunny hopping, had again been predicted with uncanny accuracy by NASA on Earth. Because of these original requirements, most of the data about human exertion in space comes from early models.
What is the human machine? It's circulation, digestion, sight, hearing, balance, its endurance.
Running, bending, climbing, and breathing profiles were developed. Today, revealing upper torso investigations are underway at Ames Research in California.
What we're trying to do is simulate the muscular activity and the metabolic rate of an astronaut in extravehicular activity, what we call EVA. And so what I'm looking at is not only their oxygen consumption, how much oxygen their body's using, but also how much carbon dioxide their body's producing, and a number of different skin temperatures, core temperature, and of course heart rate, just to keep them safe. He's not only having to work against the seat, which is going up and down, which would happen in an astronaut in EVA. He might be working up and down with his knees bending, but he's also having to work on the seat, and that the seat is going from side to side. His feet are in restraints, and that's helping him to remain stable. That with the help of the legs and the muscles in the legs. One of the exercises we're also doing is keeping this seat in a locked position so that it does not move at all like you're seeing it now. So one day he may come in and do this exact test with it completely stationary, another day with it moving. Our premise is that on the day when he is in an unlocked or moving position as he is now, he's going to expend more energy because it's that much harder to do the work with the lower body, what we call the isometric work.
This upper torso investigation is critical because in 1996, NASA's next step into space will not be to the planets, but to the weightless working environment of the space station. The space station will be built from prefabricated sections, assembled by space-suited engineers with their feet locked to the components in stirrups. They will probably wear a version of this advanced or Mark III suit. With its turtle-like plis, it is an even heavier version of the shuttle suit.
One of the features of the Mark III suit is that we had kind of taken a step away from the type of donning system that we had in the shuttle suit and went to a rear entry configuration. And basically, this hatch would have the portable life support system attached to it, and the crew member would basically come up, float, put his legs down in here, and don the suit. Prior to getting into the suit, however, when he's halfway in, he would connect up his liquid coolant garment. This would be part of the plis. In fact, we have a hinge mechanism here where we can pull these two pin elements and this whole hatch would come off. And ostensibly, with the plis connected to that, you can actually replace the plis on orbit or on the lunar surface or on Mars if you utilize this same concept. Well, although, you know, we were designing this primarily to satisfy space station baseline requirements, with the incorporation of the hip bearings and the rolling convolute waist joint that we have in here, the suit actually turned out to be a very good walking suit. In fact, we're looking at some of these technology features for application towards the Lunar Mars program when that comes about. But we'll be using features such as this from the suit for the next upgrade. We'll probably be taking other elements of the suit. For example, as we see here, it's a large torso. It's currently composed of cast aluminum, and we're now looking at replacing all these hard elements of this particular suit with a lightweight composite material.
With the suits becoming more like small spacecraft, life in the actual spacecraft has become slightly less uncomfortable. Instead of the suits being worn constantly, work on board the shuttle is as near normal as weightlessness allows. Pressurized to Earth atmosphere, breathing normally and wearing shorts, the crew offer a tantalizing glimpse of a very different type of life in space. It wasn't always like this. In the cramped two-man Gemini capsule, simple problems dogged the design of suits and the comfort of the crew. On the long spacesuited journeys, personal hygiene was a real challenge until Matt Radnofsky and Jim Coriali came up with the defecation mitten.
Matt had the idea for a defecation mitten, as we called it. It was designed with one finger in a bag and had a anti-putrefaction medicine within it, iodine and some other mixtures, I presume. I don't recall, it's been so long ago. But, of course, you unzip the suit and you place this against the buttock, and being in weightlessness, of course, stool had to be batted down into with that one finger that was in the bags. And then, of course, you wipe and stuff the wipe inside the bag and close the bag up and kneaded it to prevent it from gasifying and exploding. And funny part about it, as the astronauts ate food and reduced the contents of a food compartment, these so-called blivet bags were placed therein. All worked out fairly well.
So did the special problems women in space brought to suit design. A nappy.
We did come up with the idea of this diaper, and it really, I think, was sensational. The material we use and the products I won't get into, but it had the capability of absorbing 200 times its own weight. And we got to develop, made a diaper. In fact, I had my secretary wear it one night at home, and it worked absolutely perfect, and it left no irritation, anything whatsoever. And I believe they still use it today.
Deep inside the NASA Ames Research Center in California is a forgotten storeroom. For spacesuit designer Vic Vickickel, it contains remnants of his life's work. In here are the suits that didn't make it into orbit. They are the hard suits. Hard because unlike the hand-stitched so-called soft suits worn in Mercury, Gemini, Apollo and Shuttle, they do not inflate. Hard suits are built from lobster-like sections that rotate on bearings. This overcomes one of the main problems with the soft spacesuits. The effort, or torque, required to move the joints and hold them in position once there is minimal.
We have done detailed measurements of like the torques being how much force does it take to move the joint elements. And they're significantly lower than the technologies in the soft suit, world. For example, if you bend this elbow joint, there's no energy required to hold that arm in this position. Typically with a soft suit, it wants to rebound or restore back to some position that it only has one neutral point. That's the advantage of hard suit technology, and the fact that the amount of energy that it takes for the astronaut just to move the suit is significantly lower than the current technology in soft suits.
Hard suits are not new. In fact, work on hard suits started at the dawn of the space program, and while ungainly on Earth, promised improved mobility in the weightless vacuum of space. But as this early research film shows, getting all the joints into the right place can be a problem. The limb movement needed to align the joints became known as programming.
Programming means that if I want to flex a joint, if I want to reach here to do something, if I want to reach there to do something, I would like my nude body reach to be followed and translated in the suit. I want to be able to reach from here to here without some intermediate motion where I align the joint to be able to get to that point. And programming is an aspect that runs into, that is more likely to happen within a hard joint. Now, there are good hard joints designs that minimize that, but that programming aspect is a problem that we've seen in hard joint construction.
There is programming, but let me say this, that programming is something that you get used to very fast, in the fact that it's a matter of exposure to the suit. When we test suits, you got to realize that the astronauts have been hundreds and hundreds and hundreds of hours in the particular suit that they use. Therefore, if something else comes along, they can be very critical of it because they haven't had enough time in it. If they had had all that amount of time in a hard suit and then went into that suit that they have currently, their response would probably be the same. It's transitioning. It's like they say, if you got something and it works and it's not broken, don't change it.
The shuttle suit hasn't broken, but it is changing. It already has a hard upper torso, or hut, that the crew can wriggle into. But perversely, most of the joints remain soft and inflatable, and therefore get stiffer the more pressure is put into them. The atmosphere on board the space shuttle is similar to Earth pressure, about 14 pounds per square inch. So to get into a suit at 4 pounds per square inch, a period of decompression is necessary. This takes 24 hours as they drop the pressure inside the shuttle to 10 pounds, about the same pressure as high places on Earth, like Mexico City or Denver, Colorado. Inside the airlock, they bridge the difference to match the lower 4 pounds per square inch pressure of the suit, before opening the hatch and floating into the shuttle bay. It is rather like decompressing a diver after a deep dive. Nitrogen narcosis, or even the bends, is the risk.
When you start out from a space shuttle, which is at 1 atmosphere, normal breathing, oxygen, nitrogen at 1 atmosphere pressure, you are saturated with nitrogen at that pressure. If you want to go to and operate in a spacesuit, which is at a lower pressure outside of the vehicle, you have exactly the same problem. You have to get rid of the nitrogen. That takes time to do it safely. The choice of suit pressure then very much comes into that. If you have a suit pressure which is exactly the same as your habitat pressure, or your shuttle pressure in this case, then you have no problem. The lower you make the pressure in the suit, the more problem you have with getting rid of that nitrogen, exactly as a diver has to do.
So ideally, a shuttle EVA suit should operate at least 10 pounds of pressure. Yet if the suits used today were inflated to that pressure, they would become too stiff to work in. It is at high pressures that hard suit technology now begins to look more attractive.
With these types of suits, it's rather, and I put in quotes, insensitive to the pressure, and the fact that the performance at 4 are at 10 pounds per square inch is negligible in terms of the astronaut being able to tell that there's a difference.
Rotating at the shoulder. Reaching over.
It's on Earth that astronauts can really tell the difference. Suits are worn mostly for training and testing. They spend relatively small amounts of time in space, and this has always given soft suits an advantage.
I think 90% of the use in a suit was in training at 1G. And a hard suit is a lot, I think, much more uncomfortable. In fact, the first hard suits that I came across, and I tried one, had a bicycle seat that you had to sit on. And I don't know, I just ride my own bicycle around the street, and it's a little uncomfortable after a while, sitting on a bicycle seat.
Yeah, if you want to hold that door, Bernie.
Yeah, I've got it.
Okay,
I
arms.
just don't want it to pull on your LCG.
There is now a hard suit that is taken seriously as a contender for prolonged zero-gravity use. It is called the AX-5.
The LCG pulls it shut, so.
Okay, you still got straps if I can. I'll grab it. Okay, ready to shut that hatch?
Yeah, I'm all set.
Like the advanced Mark III, it has a hatch for rear entry.
Locked. Water in and locked.
Instead of concertinaed fabric or convoluted joints, it uses the cleverly angled, pressure-tight bearings developed over the years by Vic Vickercall and his team here at Ames.
Coming on and locked. Okay, railing coming out.
Here we go.
But the AX-5 still suffers from the same difficulty all hard suits have. It is heavy and clumsy on Earth.
Okay, I can see him now. Keep going.
Okay.
For the designers, this is a small price to pay for one major advantage over soft suits. It can be produced in large batches on modern computer-controlled machine tools.
The thing about a hard suit is the fact that you can use standard aerospace techniques for fabrication, for inspection, for materials controls. It's not an art, it's a science.
One of the things that drove us to consider more and more hard elements was the reproducibility of the materials and the reproducibility of the fabrication process, where things are made on machines, they're made to drawings, much as things in your car or an aircraft are done. So every part is very, very similar to every other part. The margin of error on fabrication and design is lower, and that tends to mean that the costs will go down. It doesn't mean that you can't build a perfectly safe and functional part with hand goods, but you tend to have a higher reject rate.
It doesn't take any black arts, any magic arts, any particular artistic capabilities of manufacturing it. You don't have to be a good seamstress. You have to be an engineer. You have to be a good metals man to do it.
Just to give you an idea of the work envelope.
And a metal man is the result. But in the weightless buoyancy of a water tank, an amazingly mobile one.
Get down just about touch my toes. The remarkable thing about this suit is that it's a constant volume suit, which means that in any position I get into, it doesn't take any effort to hold the suit there. And again, I'm showing you the work envelope here while you're in these, while you have both feet in the foot restraints. And there are certain positions where you may have to just work around a little, what's called programming of the joint. But it's very slight, and it's really just a learning curve. You might not be able to go from point A to point B directly, but you figure out very quickly how to do that. What I can do is I can show you the mobility of the legs by just bending backwards. And you can see that you can go all the way back here. The limiting factor here is the bottom of the tank.
The hard AX-5 is an Ames research project, whereas the soft suits favoured by NASA were developed in the vast facilities at the Johnson Space Center in Texas. Until recently, there was a battle for supremacy between the two approaches, but it is likely that the best features of those hard suits and these soft suits will lead eventually to a new, much lighter hybrid outfit.
We are moving in a direction of combining the best features of the soft suit and the hard suit. Unfortunately, the soft suit, hard suit issue has become somewhat of a debate, and it has somewhat polarized the community. But the reality is that we are already using a hybrid suit, and I think the pragmatists will have the day, and we will use the best elements of both.
Certain features of the AX-5 suit that was produced by Ames is superior to any other suit we have. And we are looking to see how those features could be incorporated right now into the shuttle EMU. We have no pride of ownership in terms of this is ours and this is theirs. We have pride of ownership, and we have a good product. We put an astronaut in it, we fly. And we want to get the best for the crewmen that we can afford, that meets the requirements. And if it's a piece of the AX-5 or a piece of the Mark III, or it's a piece of a Project Mercury suit, we would use it if it was the best, if we could convince the system that that's the best and the program should use it.
Neither hard nor soft technology has really solved the glove problem. Unlike the suits, shuttle gloves are custom built for each astronaut, and yet they reduce the potential of the human hand in space to the point where some have questioned the validity of EVAs at all.
If you can't use these in space, there's very little reason for you to be there. Certainly no reason for you to be outside the vehicle.
The hand is a very complicated system here. We've got about 35 different mobility functions, all of them combined, finger motion, tactility, wrist motion. So the idea is to try to miniaturize, if possible, some of those joint elements that we would have in the suit into the structure of a glove. But it's a difficult task. When we started in the program back in the Mercury Gemini period, this happens to be an old Gemini configuration glove that had very little mobility. But this glove, for its simple mobility, utilized fabric restraint with some knuckle break points here, as you can see, and then the wrist area was very simple, just a strap that would cinch down and allow you to flex and bend in a reduced diameter fabric element. Apollo gloves were not much more involved from a technology standpoint, due to the fact that, again, we were looking at spin-offs from some of the technology of the high-altitude aircraft era. The gloves for Apollo were custom designed to the individual's hand size, so it did help perform some mobility features, and also, again, being a soft material, gave good tactility as well as the dexterity of the material. The more advanced glove systems, as we got involved in higher operating pressure, relied more and more on hard structures. This was an early hard suit glove. You can see we had a rolling convolute wrist, a lot of hard ring blade elements, hard linkages, and a hard palmar structure, and we had, at that time, an internal type metacarpal joint.
Joe Cosmo's Black Museum of Gloves is evidence of the frustrating difficulty of glove design for work in space. At the moment, NASA's gloves offer little more dexterity than thick mittens, but they are thick for good reason.
To do things, you've got to touch and feel and brush against other objects, which could be rough surfaces or have potentially sharp objects, so the material has to be tough and durable at the same time. But I wouldn't by any means say that it's a fully dexterous, highly mobile, adequate glove for long-term operations in space.
Research into long-term glove use is done in vacuum chambers like this. These latest gloves do not have their thick outer micrometeoroid protective cover, and yet are already at the lower limits of useful dexterity at only 5 pounds of pressure. Hard joints make movement easier, but the more metal a glove has, the bulkier it gets. The bulkier it gets, the less use the hand becomes. This rare fragment of film from the 60s shows a completely different approach to pressurized glove design. It uses the tight fit of elasticated material to exert mechanical counterpressure directly onto the flesh of the hand.
We looked at the mechanical counterpressure glove as opposed to a full pressure glove, and basically there's a physiological problem that crops up. Because you take the basic suit, we were looking at taking a full pressure suit and then maybe stopping it at the wrist area and then continuing it with a mechanical kind of pressure glove. But then you have this pressure differential between the suit pressure and what the elastic material which you use basically in this restraint in a glove. And you find that the difference in this pressure causes a couple of problems. One is the fact that the hand's starting to swell. You get pooling because of the differential. You have lower pressure in the glove area than you have in the rest of the suit. And that's only tolerable for a very short period of time.
Made to protect the wearer from the vacuum of space, the space activity suit consists of layers of elastic cloth.
This is film of a suit that has long since rotted away.
The elastic cloth exerts mechanical force on the skin to counteract the effects of breathing oxygen under positive pressure. The Space Activity Suit allows an unlimited range of body motions. The subject walks, crawls, and climbs.
This is not underwear. This is the complete suit. Instead of air pressure, the suit uses the body-hugging properties of elastic to counteract the vacuum of space.
We looked at a full mechanical counterpressure suit. You have to have total counterpressure in all areas of the body. And of course, as you flex your elbow or under your shoulder area, under the arms and the crotch area, you have these discontinuities, and they have to be filled some way. And we find that you had to put either foam pads in those areas or some sort of a gelatin-filled bag. And so this now makes this system even more complex to try to integrate. Then you have to have the individual donning this system, and that was another problem, because these layers of material, each layer of material perhaps gave a counterpressure of somewhere on the order of a pound and a half. But it took about 2 or 3 of these layers to give full counterpressure. And so they had to slip on these layers individually, and the donning sequence was somewhat laborious.
But 25 years ago, materials technology was the limiting factor. Today, there is a renewed enthusiasm for these failed ideas, because Mars has an atmosphere of about 1% the pressure on Earth that might allow the use of a modern version of the skin suit.
Where we want to be may look something like this, to something that looks pretty much like the Buck Rogers concept, a suit that is form-fitting and a very small life support system. People have been trying to develop this concept since about 1965, and they have not been successful generally because of materials problems. However, with the biological revolution that's in process now and our ability perhaps to tailor protein molecules, there may be a breakthrough out there in the future that would allow us to make a material out of a protein-like substance that could perhaps do this job for us. And my belief is that such a suit would be considerably lighter and would reduce the ventilation requirements of the life support system and allow the life support system to come down in size dramatically.
What this requires is a revolution in spacesuit design as profound as the change from the old lead-weighted divers' outfits to today's scuba suits. Mars suits that are like a second skin might seem like space fiction. But for some, this development is simply a matter of emphasis. An emphasis on science rather than engineering.
When you begin with a philosophy that you're going to drive the design of the suit by science, you end up with a totally different package than if you let engineering go away and design something for the scientists. In Apollo and in Shuttle and projected for station, what we've done is we've taken a suit that's really evolved from the Gemini days, even before the Gemini days, starting with the soft suit concept, and let it evolve through engineering changes and kind of bolted these changes on and made it more complex and gave it more capability. But what we were really doing was starting with an engineering device and then foisting it on the scientist. There was really only one scientist who's ever used an Apollo suit, and that was Harrison Schmitt on Apollo 17. He was a geologist. And that's because Apollo was an engineering mission. Mars is not an engineering mission. Mars is a permanent habitation, scientist mission. People are going to go out, and they always say the same thing. We want to get our hands dirty. We want to get out there and dig and build, and those are the things we want to do. If you're going to do that, you've got to ask the scientists. And you've got to find out what they want to do exactly, and how much work, and what kind of picks, and what kind of slopes they're going to climb up, and how long they're going to do this, and how long they're going to do that. When you have all that information, then you've got the requirements necessary to think about designing a suit. But the last thing in the world you want to do is give this thing to engineers first. Let them build a suit for you. If a Mars mission is going to be devoted to going and planting flags and footprints, simply going to Mars and coming back and saying we've been there and bring back some samples, nobody wants to do it. The philosophy is one of permanent habitation and permanent settlement.
Ultimately, we're talking about settlement. Settlement means perhaps more ordinary people, it certainly means family. Can't you see the situation where a couple has a baby and it becomes a milestone in that child's life when it's allowed to go outside the first time in its own little spacesuit?